Well, good morning. This now seems to work, not that I need it. And this is the opening of the 2002 workshop. I think it's the eighth workshop. It's the eighth workshop at Johns Hopkins, and as Sanjeev reminds me, it's the 10th since the beginning of workshops that were invented by Jordan Cohen over there. I mean, invented means he arranged to get money for it. Which is, of course, much better than invention. Anyway, as you know, or maybe some of you know, because you were subject to it, but others don't, might be just visitors, we make quite a preparation for a workshop like this. We met sometime in November to decide what it is that the teams should work on and who the team leaders will be and so far and so forth. And since November, the teams were more or less in operation, some more, some less, and started doing preparatory work for the real kickoff, which is today. They met twice in various venues, I think mostly at Johns Hopkins, but I think some might have met somewhere else. Certainly some wished to meet in Prague, some wished to meet in Edinburgh, but things didn't work out that way. I think not because of money, but mainly because of visa and stuff like that. We had a pre-workshop in the last 2 weeks where we tried to introduce both the graduate and the undergraduate students to the material that's going to be worked on. Perhaps those of you don't know, the graduate students are people that we selected, but the undergraduates were selected in a national search. I don't know how many people applied, 100 something applied, and we have 8 here, right, with us. The 8 lucky winners. We have 4 teams that are going to be working on various problems. One team is called Generation in the Context of Machine Translation, led by Jan Hajic. Then another team called Weekly Supervised Learning for Wide Coverage Parsing, led by Mark Stigman. I've seen Mark over there. Then Super SID, exploiting high-level information for high-performance speaker recognition, led by Doug Reynolds. Where's Doug?
He's on his way.
He's on his way. So, leaderless team, and then finally, I saw Catherine. Anyway, finally, now the speech recognition models for Arabic. Catherine. I think Sanjeev is going to say more about this and also about the pre-workshop and how we had speakers and so far and so forth. In the next 6 weeks, we will have speakers, outside speakers on Wednesdays. I think 3 are confirmed, and Sanjeev will tell you who they are. They are, I mean, invariantly preeminent in their field, and they've been selected by shall we say, a vote or stating of the desires of various groups. They are not necessarily speaking about the themes that we are taking up here, but about themes that are related to what we're doing. One of the crucial things about the workshop, and it's less crucial as time goes on because people have it everywhere, but in 1995 when we started, we attracted most people by the fact that we have an espresso machine. Right now you can get espresso anywhere, so I don't know, we'll have to figure out something else that's attractive. I don't know what it could be. Anyway, the espresso machine is in the basement, and there are usually lessons on how to use it, and everybody will get a mug, and they will hopefully clean it themselves and not steal other people's mugs. The mug has a convenient CLSP logo. I want to say, sort of conclude, I was, well, every one of our 4 teams really is going to work on the basis of statistics. And this reminds me that at ACL, one of the invited speakers was Peter Norvig of Google. And he put out a slide. He put out a slide saying what percentage of work on natural language processing is based on statistics through the years. And about 12 years ago, there was 0. I mean, there was no paper at ACL which had statistics or probability or anything like that in the title. And now it is 50%, and he estimated that maybe it's 75% of papers are based on statistics. And speaking of that, he astounded me. I was wondering what do you think, how many servers does Google have? I mean, how many servers are working for us when we're searching using Google? 10,000. Why do you pick this number? Now, this is very interesting. I mean, it's mind-boggling to me, this number. But you're only the second person who I asked how many, and they said 10,000. So either this is a not round figure, or everybody knows it subconsciously, or it's the right figure. You know, I mean, that you shouldn't do it with 11,000 and 9,000. I don't know. Okay, well, so this is the opening statement, and next comes what? Next, Charles Wayne will say something.
Well, good morning. I'm just very pleased to be here. I think I've been to every. Where do I have to stand? I think I've been to every one of the workshops. You know, all 10 in one way or another. I had the distinct pleasure actually 3 years ago of spending a whole summer here, and I learned what the experience was like firsthand. I visited many times before, but the first time I actually got to be here for 6 weeks solid. And it was, so I envy all of you who are going to be here for 6 weeks solid, and some of you have been here for 2 weeks already, I know. It's a lot of work and a lot of exploration, and it really pays off. You keep seeing papers that come out of these workshops, not just the work that ends at one summer, but the work that follows you know, in several years thereafter, that build off of these things. That end up in great papers, end up in proposals that we read, and some of them we have enough money to fund, more than we would like to fund, than we have to do, but many great ideas come out of these workshops and are developed to a reasonable degree here. So I'm just very pleased with the process that goes on, and that's why I've been a strong supporter for many years of these things, of these workshops. And these 4 topics listed here are all relevant to programs that DARPA is sponsoring. I mean, they're not paying for the whole cost of this. It's shared between several agencies. But we have programs called Tides and Ears in the language area. And these map very nicely to the kinds of needs we have. And so I'm going to keep in touch with what's going on here, and I look forward to great accomplishments. And I really have very little more to say at this point. I'm going to sit down and let you guys tell us in more detail what the plans are for the teams. But enjoy the summer.
I'll just second what Charles said. I've been involved in the workshops. I've never been to one for the whole summer. I've been involved for about 5 or 6 workshops in either the planning process or the assessment process at the end. So I understand the quality of the work that's been done. I'm very excited about them. I'm a big supporter of the workshops. Driving in this morning, I was thinking about the, taking the long view of the workshops, and I think they're an extremely interesting experiment in how to accelerate the timeline of progress in R&D. It's a very, very complex process. Mixing strong elements of the NSF bottom-up model for choosing scientific problems and how to attack them, and a little bit of the DoD command and control type R&D, and a lot of the academic atmosphere that's provided by the team leaders. I think it's just a very exciting experiment, and I'm personally invested in a couple of these problems this summer, have about 20% of my manpower attending the workshops. I'm really interested in what the results will be. But in spite of all this complexity of trying to choose problems that are ripe for attack and have an educational perspective to them so that they bring undergraduate and graduate students into the community, and a technology focus to some extent. In spite of all of that complexity, there's also a simplicity to these workshops that I really like, which is that everybody has fun attacking problems that they're interested in, which I think is the essence of the spirit of the workshop. So I urge you all to enjoy yourselves working hard, and I'll be back at the end to see how you did. Thank you.
I can't take this back, it's already there.
No, I'll just speak loudly. Will that work for you? Okay. When I initially put this together, I said, look, we'll start at 9, nobody's going to show up at 9, so let me do some chit-chat while people show up, and then we'll get the real thing going. And I said, okay, pre-workshop activities, and I'm going to talk about the 2 weeks that just went by, and all the fun lectures and tutorials we had. And then I realized that, pre-workshop really means the whole year before the workshop. And guess why? At least for CLSP, the whole thing begins in September, like Fred mentioned. We put out a call for proposals. The proposals come in October. We have to do some preliminary screening, throw out the obviously impossible ones. We'll invite people for the meetings. We have to do, then in November there's a peer review meeting. We select team leaders, the skeleton team. We hope that the money comes to JHU in about December, and I'll tell you how it went this year. It never happens that day. And then we advertise for the undergraduates. By January, we finalize the team members, or at least the senior members of the team. We beg and plead with them to tell us what they will need in the summer so that we can set it up. The grad students get selected by the end of February, the undergrads by March. Then we start urging the teams to have team meetings. And then typically the team meetings happen in March, April, May. And then in June, we hope that we can fine-tune everything. This is sort of the idealized view of how the workshop goes. And you can see that while the rest of the world sees this as something happening in 6 or 8 weeks in July and August, for most of us here at Hopkins, this is something that keeps happening. Because by the way, at the end of this, the next cycle starts. So I'll tell you a little bit about what happened this year in this whole cycle to give you some, sort of to tell you how we got where we are today. So the road to the Final Four, meaning how do the 4 teams get selected? Well, we had an open call issued on September 3rd. We advertised it widely at Eurospeech, and we sent electrons. We spammed people like crazy, so everybody I know had got a notice about the workshop proposal. We got 15 proposals. Most of them came in on time. A few came pretty late, but we took them anyway. And we did some initial screening, and we don't really discourage anybody or discard any proposal at this stage. We just throw out the really, really impossible ones. So 12 out of 15 made it. And then we had a 2-day peer review meeting, November 9th and 11th. Well, that's 3 days, but I call it 2 because we start on a Friday evening and end on Sunday noon. We invite the authors of the proposals. We invite additional people who could be potential participants. We invite government program managers, and of course, my colleagues and I are there to run the whole business and potentially participate in the teams. We typically use voting. It's sort of it's the NSF for bottom-up way of getting proposals out. And we, by the way, tried like 17 different schemes this year, and I'll tell you about that as well. No hanging chats, it was all clean. And we wanted to have 3 winning proposals at the end, but we came out with 4. So we said, okay, we'll try and accommodate all 4 anyway. So who attended this meeting this time? Well, here you can see the list. The first 2 columns are researchers who are potential workshop participants. Some of them proposed their topics. And then we have in red the government program managers, and then the Hopkins faculty, and this is roughly to tell you what the composition of these meetings are. The idea is to kind of review all the proposals and get some consensus on what might be interesting topics to work on. And what were the proposals we debated? Well, here they are. Greg Baldwin had one on co-reference, Everhard Biggers had one on Arabic NLP, Louis Guthrie had one on semantic tagging, Jan Heitch had one on generation, John Henderson wanted to do speech recognition for a language that doesn't have a written form, so he figured the output should be in English. And Catherine and Jeff had one on speech processing, Mari, Catherine and Jeff had one on multi-unit speech recognition for Arabic, Drago and Jifeng Zhang had proposals on question answering, Doug on speaker ID, Rick Schwartz had another proposal also on Arabic speech recognition, and Mark Steekman had one on statistical parsing. So we debated, we argued, we had bounced ideas around for like a day and a half, and then we voted, and this is how the vote came out. So Rich sort of merged his proposal with Catherine's, with this one, and Catherine became the team leader for this. Doug's proposal, Mark's, and Jan's, with minor modifications, pretty much made it through. So these were the 4, and the reason we had 4 is because, depending on how you counted the vote, each of these would in turn, the rankings would shuffle, but these were clearly the 4 best proposals, so we decided to go with all 4. Then started the team composition process. So we got the senior members of the team more or less fixed by Christmas, the grad students in Jan Feb. So far things are going on schedule, right? So we have the grad students and then the undergrads in March. And this is how the workshop looks this year. We have 37 people. This is the biggest workshop ever. If you break it down a few different ways, there are 20 senior researchers, 17 students. The 20 researchers are essentially 12 from academia, 4 industry, 4 government. The students are half and half grad and undergrad. And these numbers are tentative. I haven't got, by the way, everybody needs to send me back those survey forms with your bibliographic information. We need to do some reporting on that. Okay, we also have this year, by the way, I'm not counting people like Joe Campbell or Mari and Dimitra Vergheri or I think Bonnie Dore and Dan Gildea, who are tightly affiliated with the teams working with them but aren't here all 6 or 8 weeks. So this is an even bigger workshop than you think. And I think I wanted to make this comment for people who are funding this workshop, that if you add up just the number of hours these people work, I think it goes to something like 7 or 8 man-years. So, you're getting good value for your money. And by the way, I'm just assuming like an 8 or 10 hour day, and you know how people work in the workshop, so it's actually much more than that. And I'm not counting all the administrative work we do. Anyway, so each team had face-to-face meetings. We encourage it because, as you can imagine, the 6 weeks is very intense, and we need to prepare for it early. So the teams met. First off the blocks was the generation team, followed very quickly by the super fit team, then the Arabic ASR and the parsing team, and they all met, talked about what they wanted to do. And that essentially brings us to July 1. There were a couple of data contracts that made their way through the works. We have some new annotated data coming for the generation translation team and some markup data from SRI for the speaker ID team. And just to tell you how the money moves, it left DARPA for NSF in March. It got to NSF sometime in May, I'm told, and it hasn't reached us yet. We are hoping that it will get here this week. But things move along, and this is sort of how the government works. Oh, the other big factor is when do we write the final reports? I won't name anybody, but we are still waiting for one report from last year. So things go off schedule once in a while. All right, so what have we been doing for the last 2 weeks? Well, we've had a summer school. It's a 2-week tutorial on various aspects of human language technology. And we initially started organizing them mainly for the undergraduates. In '98, we started having them. We said, oh, these kids are clueless. We need to bring them up to speed. And then we realized that a lot of other people were interested in these tutorials, mainly from DoD. And this year, we have special interest from NAACL. they're sending us a bunch of students, and they'll probably do this for another couple of years, I think, where we have another 9, 10 graduate students or undergrads who are paid for by NAACL and who come to attend these tutorials. So that resulted in another record attendance. We have 37 people this time, undergrads, grads, and some researchers. And we essentially had to get a big room. We couldn't fit in our lecture rooms in Barton Hall anymore. And so this is, if attendance is any mark of success, this was another successful exercise. So what do these people do? Well, here's what they did. They heard from people like Eugene Charniak and Al Gorin on the natural language processing, and Jason put together a nice lab for them in the afternoon. They heard from Jim Mayfield and Donna Harmon. The blue things, by the way, are lectures, and the yellow stuff at the bottom is labs. So then they went to the lab and tried out a few information retrieval exercises using the engine or NG. We had a day on machine translation, Kishore from IBM, Daniel Marco from ISI, and David put them through a tutorial using the Giza machine translation tools developed here at the workshop 2-3 years ago. 4th of July, we gave them a day off. They went to the mall in Washington, saw the fireworks. We had a day on generation. We had a day on speech recognition. Bill put them through the resource management toolkit exercise in HTK. So all the students have had some experience building a speech recognition system. Francis Kubala told them about the BGM on-tap system. By the way, if you notice, there are 4 days, 1 here, 2, 3, and 4, where the days are dedicated to what the 4 teams are doing. So the idea would be that although these students are in individual teams, by the end of these 2 weeks, they have a good idea of what all the teams in the workshop are doing. So this is a good education exercise for them. And then on the last day, we had fun with dialogue systems. We had Lynn Walker from AT&T, Roberto Peracini, and they showed how some of this technology is being commercially used for telephony-based dialogue systems. Well, that's the end of the 2 weeks, which brings us to today. And while the 4 team leaders will tell you what will go on most of the time over the next 6 weeks, which is research and more research, there are lots of other scheduled activities that, especially those of you who are not in the workshop but visiting, might want to take note of. So we are, of course, over here today at the opening ceremony. Every Wednesday in the mornings, we're going to have seminars. As Fred mentioned, we have 3 of the speakers lined up. Andrew McCallum, who used to be at Bank, he's currently in between jobs, I'm told. He will give us our first seminar this Wednesday. Then we have Fernando Pereira from UPenn coming here on July 24th, and Joshua Bengio from Montreal here on July 31st. We're still trying to nail down the 2 speakers. There are invitations out, and hopefully by the end of this week, that name's there too. Every Thursday we have an optional group dinner, so if some of you are in the area and just want to hang out informally with teams, you can join us then. Here are the key dates to remember. The final presentations, they will be in August 21 and 22. These will be full day presentations. Each team gets about half a day to talk in all sorts of gory details about what they did over the summer and all the interesting things they found, all the lab results. Then Friday is for lab cleanup, which means both physical cleanup of the space and cleanup of your file system, directory structures, packaging cleanup, so that we can continue the work well after the workshop. So this is what we are looking for. But more importantly, the part which is not said here, there's going to be lots of research, and now the 4 team leaders in order will come and tell us what they're going to do. So first up, I think, is Jan. Is that right?
I will try to. Okay, good morning. Yeah, I'm scheduled, but I will hope it's only my 15 minutes of time. let me first introduce the team we have. And as you have heard, we also have some affiliate members on the team. This is the complete list. Radev, please, from Michigan, who has a great experience in natural language generation. Joe Chen, Joe, from University of Toronto. Jason Eisner. Jason here? Jason, you know Jason. Owen Rambo, right, from UPenn, and Don Gildea and Bonnie Gower, well, Bonnie's coming in the afternoon, I guess, are the affiliate members of this team. And then we have two graduate students, Johan Ding from UPenn and Martin Schmerek from Prague. And also the two of the 8 winners, Carrie Cook and Kristen. Okay, so this is the people. Now, what are we going to do? We are doing natural language generation, but let me say at the beginning, not to confuse things, that usually what's meant by natural language generation is the whole way from some logic representation or some action schedule to go in 2 steps. First, to actually plan how the natural language sentences should look like, and then generate the surface form of the sentences. Now, what we want to do is to do generation in the context of NT, which means that the first part is actually not there, because we already know what was said in the other language. Of course, we see obvious problems of translation, but that's where we want to start. We already know what should be said, and we have some kind of syntactic, semantic representation, well, all we can get from the other language. So we would like to go from there, and we call the representation we want to use a tectogrammatic representation. That has been developed in Prague over the years, and we believe it's a suitable representation for machine translation, but not only for machine translation, but actually we believe it can be used as exactly this intermediate representation for any type of natural language generation, like for generating answers in question answering systems, or for the real generation from databases or web. Then of course, as always requested, we want to evaluate this is the whole generation system, or actually the whole machine translation system. And I will talk a little bit about that, because evaluating generation is always kind of difficult. So what is the virtual NT system setup like? So we assume there is a classical scheme of an NT system having analysis and transfer and generation. And what we propose is to use the tectogrammatical representation for the transfer stage, for the actual translation, and then generate from there. Now we will go from Czech to English, because there's the 2 languages. For that we have the resources to do the whole thing. So this is the same thing, just in some graphics. And again, here is the analysis step. Here we have the transfer, and this is the part that we are actually going to do during the workshop. Now, we are not claiming that the representation we use for the transfer, or as the input to the generation, is any kind of interlingua. But as far as we know, this is the deepest type of syntactic representation that has been used for machine translation or for the purpose. So it's that's what this second arrow should show here. That actually what's normally meant by parsing ends somewhere here. It gives you really the surface form. This is a deeper structure. So let me show an example of such a representation. So this is a real sentence from the Wall Street Journal. It has been, I think I just cut he said or something at the beginning so that it fits the screen, but otherwise it's a real sentence. This is a dependency tree for both the Czech translation of that sentence and the English sentence. Now, if you look carefully, I spare you those 5 minutes, but these two trees are almost identical in their structure. The only difference is actually this one node, and that corresponds to a term that's called, to wrongly inform is better said in English by misinformed. So, apart from terminology, these two trees are the same. Now, again, we don't claim this will happen all the time, but we have made some experiments in the pre-workshop period, and we found that for a technical type of translation that can apply to the economic news as well, this is very often the case. It's 80 to 90% of cases. The trees are the same except for the terminology. So in fact, this will be the input structure to the generation step. We just assume we can do the whole thing from the check representation, and this will be at the beginning. So what you can see here that many of the words or the nodes that can be seen normally in a surface parse tree are not present here, like prepositions, right? For example, about financing. I mean, there is no preposition here, and it's kind of replaced by the function of the word relative to its head word. And similarly, according to his opinion, again, according to is replaced by the function of the word. Also, it was passive, so there was no actor. The actor is added so that it corresponds to the other language, just in case the actor is expressed in the tree. So I won't go into details. We will give updates as we go, and we'll show more of it. Now, just for comparison, these are the dependency versions of the surface parse trees that you can get by today's parsers. And you can see that even though they are not that far away, they are still quite different. Well, first difference you notice is the word order, because for example, this auxiliary verb here is more to the left in the original. Also, the preposition according to is expressed by just a single word in Czech, and also here we have a preposition in English, but there is no preposition in the source language. The preposition is in fact expressed by inflection here. So we thought that even though there were attempts to do translation of such trees, and I think it has its advantage to the plain word-based translation, the correspondence is not so obvious, and that's why we have chosen the representation for this. Now let me just note that actually I'm still talking about generation from the deep level, but in fact going from here to here is actually trivial. So we can't talk about generation from here. That would be like a 2-hour workshop, right? But what we want to do is actually go from the deep representation to the surface one, and then the rest is, well, it's not quite trivial. You have to do morphology and stuff, but it's also almost trivial. So what are actually the key issues here? If you go from the declinative representation. First of all, it's lexical choice. Now you might say, okay, lexical choice should be done on the source side. It's here because first of all, we don't have a good words and disambiguation for Czech, but also sometimes it's better to leave it for generation, and there should be some kind of a language model that will decide that. Then of course, what I call the auxiliaries, like the prepositions, conjunctions, complex verb forms based on tenses and so on. So we have to kind of insert some of the words that are actually not present in the deep representation. Then of course the word order, that's always a problem, and the simple problem of English morphology. So what do we have now at the beginning of the workshop? So we are translating, that was part of the pre-workshop activity, we are translating the pen tree bank into Czech so that we have test data, and hopefully we will have enough to do some kind of baseline experiments also with learning from the two parsed corpora. For the Czech side, we have the tools available. even though the deep parser, that's not part of the actual workshop, that's just a rule-based type of parser. But let me just point out that we have actually used the results of the previous workshop, because for the parsing we are still using what we have developed here 4 years ago for the check surface parsing. Now, we also have a translation dictionary to do the actual transfer, and what for testing we are doing the deep cryptographic annotation of the pen tree bank, at least of some part of it that can be used for testing. Then, of course, we have taken over some English morphology, and we also have the evaluation software, which is in fact a very short script. Now, let me just show what I mean by lexical choice. Since we do not really have the full MT system in place, we can't do the lexical choice on the surface side nor on the transfer side, but what we can do, we can generate several translations like here or here, and then let it decide at the generation stage. So now I promised last thing is the evaluation. So we actually plan to do a lot of evaluation. First of all, we decided to use the blue evaluation that was developed by IBM, and that's actually something that for the first time can be used for an automatic evaluation of natural language generation system. That includes translation as well. Of course, that has been developed for translation, but it can be used for any type of natural language text. And that's kind of a free text, and where you cannot really say exactly what is the correct sequence of words. So for that, we are actually translating back the sentences from the pen tree bank, and we will have about 500 sentences translated in 5 variants, so that we can actually use the software, because that needs several different translations to show objectively what progress is. Now we will have kind of 3 tracks, whereas the last one is still with a question mark, but the first 2 are here. The first one will be, we will just get the English manually annotated sentences in the deep representation and try to generate from there. That should be easy. That should show up what the upper bound for our system is. Now, of course, then we want to do the whole system, so we will start with the check sentence, and we will do all the parsing automatically, the transfer as well, and then we will generate from there. That's, of course, going to be much worse, but we would like to see it in the whole context. And then perhaps we will also try to do it from the proposition bank, but we still have to discuss that, what exactly that means, because do it directly from the proposition bank is actually easy. But to go through the deep syntactic level might be more difficult. Now, we will also have another dimension here for the generation. We will try both a statistical system that will be developed during the workshop, and a rule-based system based on the FUP, natural language generation for English, that's been already developed previously. And then, of course, at the end, so we would like to compare it with a word-to-word translation system to see whether actually all this extra work by analyzing the source language and generating the target language is better than to take the GISA, Egypt, IBM-like system and just do the thing. That's actually why we are translating the pen tree bank also, because we can train on it, we can train on some older data and see whether it comes better or worse. That's it.
We have plenty of time for questions for Jan.
Yeah, I've got a question. You mentioned 250K. What was that?
I mentioned what?
Okay, so when you talk about the translation of the pen to cherry
Yes.
stuff, you mentioned some number, 250K.
Yeah, that's what has been translated so far. I mean, we got resources for the translation, and in fact, it's quite difficult because it's economical news from the early or late 80s, early 90s, and sometimes people have to go back and check what actually happens to understand how to translate it.
Words or sentence? Words or sentence?
No, 250. 100 words are translated now. We have the translation for those. 250,000.
Of words.
Of English words from the pen tree bank are now translated into Czech. Now, we have another 100,000 that are being translated now, and we hope we will be still able to use it during the workshop. And that's it, what we could do with the resources we got from the workshop. Actually, we will continue translating the pen tree bank using our own resources. That will probably go slowly, but sometime next year we should have the complete translation for anyone who wants to do experiments with that.
I had a question. When you say complete translation from Czech, so I assume that you already have some system for doing the deep syntactic analysis on the Czech side. What are you doing about the transfer?
Well, at this moment, we don't have any statistical transfer because for that we need the translation to be finished first. But what we do have is a statistical tagger, a statistical parser to the surface dependencies. Then we have a rule-based system that goes to the tectogrammatical level. And then we have a translation engine that's actually doing nothing. And that keeps the structure of the Czech, just moves it onto English. And the only thing it does, it looks up the words in the dictionary and assigns several English words if there are several translations. Or it will be able next week to do also the term translations. We know this looks like we are looking at the dependency structures, at the deep structures, as if they are completely the same for English. We know they are not, but as I said, in 80 to 90% cases, we think they are. So we will see what comes out of this simple system. Because actually one of the claims is that by doing all this work with the parsing and the generation, that the transfer can be minimalized. And this is as minimal as it can get because you don't do anything with the structures.
So will the transfer of the dictionary lookup use any of, for example, the part-of-speech tags, or will this just be a flat translation?
No,
the six translations, you just put them all in?
Yeah, you just get all of them. The part of speech is already non-existent at the deep level.
Right.
You have the words and whatever is kind of statically associated with them. You know what's a verb, what a noun is, but all the morphology is gone. You have the functions. Then the other words are gone. So it's really just a simple lookup at this point. We know it should be done better way, but that's how it is done. Yes?
You mentioned ambiguity in translation arising at the word level. So you're also going to generate more than one translation syntactically for the same set of words, or do you do it just one?
Yeah, we believe we are able to do that. There was this word. This is actually a screenshot of the visualization tool we use. And as you can see, we can represent text forest in it. So if we can do it for words, we can do it for structures as well. So as far as the real generation set is able to handle those, yes, we want to do that.
No. I say if we're done, we're done.
Okay.
Let's just move on. Next comes Mark, right?
No, of course it's gone to sleep. Is on? No, slow launch.
Press it all the time.
No, it's actually having to reboot. Okay, this is a project on semi-supervised training or weekly supervised training for statistical parsing, the cost of thousands. Here's our team. The color coding indicates the people with PhDs, the graduate students are green, and the undergraduates are in red. And this is the core team with Anup Sarkar from the University of Pennsylvania. Anup. Miles Osborne from the University of Edinburgh. Rebecca Hua, University of Maryland. And Stephen Clark, University of Edinburgh. That's Steve. Julia Hockenmeyer is also from Edinburgh. Paul Ruland from here at Johns Hopkins. Steve Baker, Cornell. That's Steve. And Jeremiah Krim, J. Krim from Johns Hopkins. Okay. We also have some associates. We're very pleased to have the advice of John Henderson, who's working on a different project. Where's John? Oh, that's John is working with a different project, but you'll see why we're glad to have his advice. And Chris Callison-Birch, who is a graduate student intermediate between Stanford and Edinburgh, is going to be a sort of part-time student, and in particular is going to help us in the first week. Chris, is Chris here? Okay, Chris is arriving today. In November, we proposed to bootstrap more labeled data from the million words of the Penn tree bank using weakly supervised techniques, which I'm going to specify in a minute, with the aim of creating very large tree banks to build better parsers. There is no alternative to labeled data, at least there's no alternative that anybody has yet proved for building statistically induced and statistically modeling parsers. But there will never be enough data. A million words of Wall Street Journal tree bank is just not enough. So what we propose is to use weakly supervised techniques to use the parsers that exist to produce further tree bank, further labeled data, using ideas from voting, co-training, re-ranking, etc. And in fact, the project has focused upon co-training, although we are taking ideas from all of the above. And all of these techniques reduce noise and produce the more high-quality labeled data. And high quality means better than just running your parser and using the trees that the parser produces indiscriminately. And of course, more labeled data gives us better parsers, and it gives us better parsers mainly because it gives us better counts, especially word counts, lexical statistics. So here's the sort of general purpose weakly supervised training algorithm, where we have a million words of labeled corpus which was used to produce our parsers in the first place, and we have lots and lots of unlabeled data, both of the same kind, Wall Street Journal, and of other kinds, particularly in the news corpus. What the technique that we're going to follow, co-training, does is to label the new data to produce new trees using several models. And then, if the parsers are regarded as being reliable according to some criteria, then you add the parsers to the training data, you retrain the parsers using the extended data set, and you then validate using the held out set, which in our case is going to be section 23 of the tree bank. In a final stage, you can do a final check, which is to see that the performance does not degrade. In other words, that the retrained parser is actually doing better than you did before. And at that point, you accept the newly labeled data and iterate the loop. And reliability can be assessed by co-training. Co-training is a criteria according to which you have several parsers looking at the data, but one of the models is extremely confident because it is a model that is good for a particular kind of data that is exhibited in the particular sentence that you're dealing with. Another tactic is voting, which John has written seminal papers on, where you use as your criteria that most of the models, the different parsers that you're using, agree on the parse. Okay. So here are some details of the project to come. there are three distinct parsers or parser groups that we're using. One is treebank CFG parsers of the kind that's familiar from the work of Collins, and Collins in particular is the one that we've worked with most, and of course Gene Charniak as well. We're also using parsers with more expressive grammars, including the tree adjoining grammar parser from Penn, which has already been used in one co-training experiment by our colleague Anoop Sarkar. We're also using combinatory categorical grammar parsers, which is another actually closely related expressive grammar framework, and this has been developed at Edinburgh by Stephen Clark and Julia Hockenmeyer. In the proposal, we considered a wide range of reliability heuristic assessments, but we focused in this task on co-training, and we're going to do two kinds of co-training. One is an experiment that's already been done by Anoop, where we co-train. Co-training always involves at least two views from two separate and unrelated models. And the simplest technique is to take a parser and what's called a super tagger, where a super tagger is exactly like a part of speech tagger, except that the categories that it predicts are from the richly expressive grammar, the 500 or so primitive trees of tree types of a tree adjoining grammar, or the rather similar number of categories for a categorical grammar. There are around, it depends on the parser that you're talking about, but with Julia Hockenmeyer's parser, there are around 1,200 category types in a categorical grammar. This means that these two grammars here, tree adjoining grammar and categorical grammar, do a sort of trade of richness in lexical types from the 50 brown parts of speech to around 500 to 1,000 more informative types, as opposed to rules in the context-free grammar, where the Collins grammar has around 1,500. Julia, how many?
About 12,000 rules or so.
Yeah, 12,000 production rules or rule types, whereas the equivalent reductions or syntactic rule types in these grammars are a much reduced set. The more interesting co-training tactic is to use proper grown-up parsers, maybe the tree adjoining grammar parser and the CFG parsers, to produce the different views of the unlabeled data. As unlabeled data, we're going to use the labeled Wall Street Journal corpus to train the core parsers that we start with. In other words, I mean, a familiar example is Collins' parser, which was trained on that corpus. I'm using the standard tree bank million words of tree, and we're then going to use unlabeled newswire corpora. And in particular, we've been using the North American News Text Corpus, which is around 500 million words of mixed origin American newspaper text. Aims and objectives. Here are our research questions. We're interested, these techniques hold out the promise of being able to train better parsers using the limited labeled data that we have for English, but also training parsers on languages where we possibly have very little labeled data and can only afford to produce small amounts of data. So we're intensely interested in how weakly supervised techniques scale with different sized training sets and different sized data sets. And we're also going to be looking at the way in which this technique can take a parser which is trained on one genre of text, perhaps the Brown corpus, and then transferred to another genre of text, perhaps news text. We're interested in how we can mitigate the effects of noise on weakly supervised techniques. Clearly, if our parsers are unreliable, then the data that they produce will be noisy, and we have to find techniques of excluding errors, excluding the noise. We're also interested in the possibility of deciding ahead of time which labeled sentences are likely to yield good information with the parsers that we've got. So we're interested in how we sample unlabeled data as we go around the loop. We're also interested in a technique that has never been investigated yet in the framework of co-training, which is whether we can bootstrap confident local parse decisions, perhaps a noun phrase that we're particularly confident about, rather than just looking at global confidence measures on parses of full sentences, which of course in the Wall Street Journal are very complicated objects. We're interested in finding out which weekly supervised training regime is best for our task. We are going to concentrate on co-training because we have some preliminary results in that direction, but we will be talking to John in particular about other techniques that we should be considering. And now I'm looking beyond the extent of the workshop. We will, in the workshop, be almost exclusively concerned with co-training. And we're interested in how efficient the weakly supervised techniques are for different grammar models. One of the reasons for looking at this wide range from context-free grammars to categorical grammars is to see whether these techniques differentiate those systems, those grammatical formulas. The ultimate, I'm going to distinguish between the ultimate payoffs and the deliverables that we expect for the workshop. The ultimate payoffs are very attractive indeed. First of all, improved coverage of improved performance for wide coverage parsers that we already have. Those parsers show signs of asymptoting at around 90% on the parseval measure, itself a very generous and tolerant measure, so that's not a very good performance. The attraction of more data is that we can possibly improve that performance. We see ourselves producing, in probably not within the scope of the workshop, but in the weeks and months after the workshop, a specimen large tree bank. And in particular, what we will choose as a criterion for succeeding at this will be producing something larger and less noisy than the brown 30 million words that Charniak produced by just running his parser over that stuff once. And that was a key result in starting us on this investigation. But Blip is really far too noisy as a corpus to use for this task. Although Charniak did get a tiny improvement from training on it. We see ourselves most usefully as producing reliable methods for building very large tree banks, but also reliable methods for bootstrapping parsers for novel genres and ultimately exotic languages, languages for which parsers don't exist, from small labeled data sets. As I say, these are all ultimate payoffs rather than the immediate goals. Our immediate goals are to use unlabeled data to improve parsing performance on Penn Tree Bank 23 for a range of parsers. And our evaluation there will, in the case of CFG and tag, be well, in the case of CFG will be the standard parseval, and in the case of more expressive grammars will be not only parseval, but dependency recovery of dependencies related to interpretable structure or semantics. We will investigate porting parsers to new genres, and our experiment will be to train on the Brown corpus, and then to co-train and test on, to co-train on unlabeled Wall Street Journal text, and to test on Wall Street Journal 23 to see how well we've managed to improve, to transfer the training on the Brown corpus to the new set. And of course, this is a sort of thought experiment or a proof of concept for the for porting these parsers to for porting the best parsers that we have, the Wall Street Journal parsers, into new genres as well. We also regard an important deliverable as to discover how small the labeled set can be and still seed an effective co-training. This is directly related to producing parsers, effective parsers for languages that large data sets don't exist for. So here's what we've been doing. I'm going to sort of talk about progress so far in terms of the infrastructure. The first bullet has really been dealt with by Sanjeev. We established a mailing list and a web page. We've actually had 4 meetings because we discovered teleconferencing being a widely distributed group. And I recommend this in future. I think you actually ought to encourage widely distributed groups to use teleconferencing, because it really was very effective, and it meant that we didn't waste man hours getting over jet lag and dealing with strange cultures and stuff like that. We designed, more to the point, I mean, in terms of scientific infrastructure, we designed and implemented a common framework and basic architecture for all the co-training experiments. We've got a lot of parsers and a lot of different outputs, and we designed a common framework, including cache management for going around the loop that I sketched earlier. And this accepts parser output from all frameworks. So we actually have a framework where any two pairs of parsers can actually get together and co-train. Some pairs of parsers are going to find that easier than others, and in particular, the categorical grammar parser has very different output from everything else. We cleaned, tokenized, and tagged the 500 million words of news corpus. And this was actually a very substantial task that took a great deal of time and a number of iterations, because there's a large amount of noise in the corpus, despite the great efforts of linguistic data consortium. So we really had to sort of iron out a lot of problems to do with slight differences in the way the different newspapers had ended up appearing in the news corpus. We brought all parsers, including the imported ones, such as Collins, and matched them to the data sets. We ran them on the news corpus and most of them on the Brown corpus as well. And this involved quite a lot of preliminary work as well. In particular, we had to actually modify the Collins parser to make it do re-ranking and retraining, and all of this has been implemented. We thought about doing this with the Charniac parser, but in the end, we felt that wasn't going to be, we weren't going to be able to get that to work in the time. So we actually abandoned that, which is sad. All parsers have been used to parse. Once we got all that done, we got everybody to set their parser running just to parse as much news corpus data as they could do in the time between getting it finished and coming to the workshop. And all of these parsers have parsed substantial amounts of unlabeled data in preparation for one data point in the co-training, which is the one where you have a large cache of unlabeled parsed data produced from unlabeled data to produce one of our co-training benchmarks. That'll actually be our final benchmark when we've got some other things going. We've done some pilot experiments and baselines, and I'm going to do these parser group by parser group, because the initial thing to do is to get parsers to produce the data, and we've looked at two effects. One is self-train, what we call self-training, which is essentially the Charniac 1999 and 1997 experiment, where what Charniac did was to take his parser trained on 1 million words, run it over 30 million words of unlabeled text, and then retrain on the trees that he produced. Okay, that's a very simple sort of base case of, it's not even co-training, it's training on your own output, on the output of a single parser. He showed a very slight improvement in the performance of the retrained parser. So this shows that there is actually information in the trees that are produced even by one parser, and mainly what it shows is that the lexical counts are improved by going over that much data. So we asked all parsers to try and get do a basic self-training baseline, and this was done with the CFG parser, the improved Collins, which was modified to do, as a matter of efficiency in retraining, was modified to do re-ranking. In other words, instead of reparsing, in the training phase, instead of reparsing the original 1 million words of tree bank, the parsers that were produced were simply, of data, the parsers were simply re-ranked by the improved model. A self-training experiment with these parsers showed a slight positive effect, reminiscent of Charniac's experiment. And co-training using both of the versions of the Collins parsers, which that group can tell you about, I'm going to pass over this for reasons of speed, has actually begun. We don't have any results from that yet. The CCG parser, to make a CCG parser involves transforming the CCG tree bank, the pen tree bank, into a CCG version, which Julia pioneered. And in the time since November, we've done a substantial amount of work to improve the CCG tree bank, so it's now much less noisy than the original tree bank, to induce a tree bank lexicon, which in CCG actually is the grammar, and to train a super tagger, in other words, something just like a part of speech tagger, but which predicts which of the 1,200 categories, category types allowed by CCG are most likely. The normal form parser that Julia designed has also been improved, and we've been presenting results from this at various conferences this summer, including a couple of papers at ACL. We did a super training, a co-training experiment using a CCG grammar, Julia's grammar parser, and the super tagger that Stephen Clark developed. And this shows a slight positive self-training baseline, again reminiscent of Cherniak's result. So these things are sort of working, and they're working as well as anything else. There is a co-training positive effect of around 5.5% improved super tagger accuracy using a small 9 million word set of unlabeled data. And the interesting thing about this experiment was that it included not only new Wall Street Journal data, but also non-Wall Street Journal data from the tree bank, from the news corpus. We found a smaller co-training effect for the super tagger just on the non-Wall Street Journal text. So this actually suggests that the porting experiment may well work. And we've begun some experiments on sample selection. Very quickly, the same thing for the tag parser. The LTAG parser has also been improved. It's the only one of our systems that has a substantial co-training effect on a small training set. This was a paper that Anu produced last year that was an inspiration towards the specification of this project. And there's a slight negative co-training result from using two versions of the LTAG parser. This is actually to be expected because the views are too similar. And a lot of work has been done preparing to co-train this parser with the CFG parsers. In the workshop, we're going to do the following experiments. I've just got 2 slides to go. We're going to investigate the selection criteria for including unlabeled sentences in the sample. We're going to investigate the effects of confidence estimates for including new parse trees in the training set, to extend the training set for co-training. We're going to calibrate the co-training effect with labeled seed data set size. This is an experiment that I referred to earlier. We're going to do the cross-genre porting experiment, training on labeled brown corpus, co-training on unlabeled Wall Street Journal, and testing on 23. And we're going to get at least 2 parser groups, and at this stage it looks as though it's going to be the CFG parsers and the LTAG parsers to co-train each other. I think I'm going to stop at that point and take questions.
I have a question for you. You mentioned that the retraining gave a 0.5% increase, accuracy increase. What's the baseline accuracy? 80%, 90%? When you get a 0.5% increase, what was it over?
Steve, you did this.
Yeah, so for the super tagger, the baseline is around
89.
So we're right up there. So.
One of them is more common. In the very basic loop you mentioned about co-training, there was this one step where you see if it improves parsing on a parser on an LM set. And then of course you want to evaluate this whole co-training as a procedure. And that's going to be also, so I'm hoping you make sure that these two are different sets.
Oh yeah, sure.
The second question I had was actually more to do with small data sets. You said that you're going to try on small data sets, see what's the smallest where co-training sort of hits the mean and takes off.
Mm-hmm.
I was thinking that perhaps because languages are so different, the benchmark to have is not data set size, but parse accuracy. What parse accuracy do you need to achieve before code training kick in.
Yeah, that's a good point.
So I
That's a
don't
good
think,
point.
is there any chance you could try this on another language, which is,
I don't think we can do that in the time of the workshop. Anoop wants to comment.
I just wanted to repeat the question.
okay, sorry, my question was that when you start looking into small data sets, it perhaps is meaningful to ask the question, what is the least accuracy you need to have on labeled data
Yeah.
before code training takes off, rather than what data you need. And I was thinking that perhaps the Czech, Jan,
Yes.
the Czech tree bank is quite large, and perhaps that might afford you another alternative. Because it's like, the language is significantly different, there's lots of morphology, and perhaps there we might see that it's not the
We-
size, but the accuracy.
Yeah, we certainly agree that size and accuracy sort of go together, so both of those measures will be taken. We started talking to Jan about using the Czech parser. I don't think we'll have time, or even machines enough, to do it in the space of the workshop. That's really, our limit is actually going to be machines. And we've been using a large Beowulf cluster in Edinburgh, and we may continue to use that as auxiliary. But I suspect that this is going to be for later.
What is ultimate parsability? I mean, you're never going to get 100%, or if you put 100 grammarians in a room and got them to form a consensus, or?
That's a deep question. We are assuming that the limit that we're seeing, Parzival results are definitely asymptoting at around 90. We believe that the results that we're seeing are, to some extent, due to the size of data sets that are being used, and we want to do something about that. But that's undoubtedly not the only factor that is holding us back. I know if you want to come.
So there's some experiments where you take the top 20 or 30 parsers from a parser, and then you have an oracle that picks the best one, and you can get up to between 94 and 95% on the current standard test set on the tree bank. And so that would be the upper bound, is if you could get up to 94.5.
But there's some sentences in the world that must be unparsable, right?
Sure. No,
What fraction of?
for us, English is the tree bank. So, yeah.
What's the general English?
So for us, we're focusing on a particular task. We're getting better numbers on this particular test set. And that's a full short side. That's what we have.
We can't really evaluate anything else, so we just have to go with that.
It sounds like the other side, so that was the question of how close we might be if we could choose the best one of the 20. But the other part of Tom's question was, will people agree? So if people can't agree to better than 95% accuracy, in some sense it's not meaningful to shoot for anything better than that. That is, there, perhaps parsing is not a real,
Yeah, and ultimately, we will have to move to tasks like question answering and what have you.
Well, no, I mean, but there's a question of if the task can't be defined, then you have to. So I guess my first question is, what is that accuracy? Is it 95% agreement between people who agree on the rules of how it's supposed to be done, and then that would raise, if it's low, that would raise the question of.
Any kind of labeling you have inter-annotated disagreement, I don't see that as a problem with parsing.
So what we're trying to recover is what is in the tree bank. So there's lots of questions coming in. Fred was.
Well, I was just going to comment that, of course, whether people agree or not depends what's in their head. And it's not like speech recognition where more or less you can find out what somebody said, or at least you can ask him what he intended to say.
Right.
But here, various people have various theories and think that certain things should be attached somewhere and others think it should be attached somewhere else. And so, I mean, when we in 1970, maybe 4 or 6, did for the first time tagging by Markov models, we had, of course, people who first tagged it by hand. And there, the inter-agreement had a 3% error, all right? And tagging, of course, is much easier than parsing. And even there, we had a 3% disagreement.
Right.
That's the sort of answer I was looking for.
You mentioned that you abandoned the attempt to re-rank and retrain using Charniak's parser. I was wondering whether that was just due to lack of time or whether you found something about Colin's parser better for that task.
It was just a matter of lack of time. I mean, it was just lack of time. I mean, there was, Charniak's parser is a complicated beast, and we weren't going to be able to do it in time. Okay.
It sounds like you're using parse-eval measures to do the comparison, and following up on the question of inter-annotator agreement, I was wondering why not unlabeled dependencies, which might also make co-train easier in some respects, where different parsers disagree on the analysis.
Yeah, I mean, we're set up to do that already. We're already using that on the CCG parser, so we will be producing both measures.
Good.
That's the one I'm most interested in.
Okay, I declare a break. And I'd like you to come. I mean, we've essentially caught up. I mean, we were ahead, but now we're more or less caught up. And, well, okay, so maybe we should start a little earlier than 10:45. Maybe we should start at 10:40. And this will give you 5-minute extra break. So how much more would you like? Moving right along, we'll have Doug Reynolds. Why don't you just stop?
Yeah. Ignore the fact no one's listening.
That's fine,
yeah. I'm used to that, actually.
I mean, there's no difference.
It's kind of like C-SPAN. Keep the camera on me and don't look at the audience. You're okay.
Just read it into the record.
Outrage. So I'll get rolling on this. I'm going to describe a bit of an overview of the SuperSID team that we're going to be looking at exploiting high-level information for high-performance speaker recognition. I assume some people have already heard, or you can see on the website, our team. We actually have a very good team this year, I believe. Excellent senior members and students, a large number actually of people that are interested in this. We've had a lot of feedback coming from different sites in here. Our senior members are Barbara Peskin from ICSI, myself from Lincoln Laboratory, Jerry from IBM, so we have a good cross-section, some academic and some research laboratories. Jill Campbell, a colleague from formerly at DoD, now at MIT Lincoln, and Walt Andrews from the DoD. We've got some very good graduate students from Andre from OGI. People can show themselves. David from Charles University, Passaic, and Shin from CNU. I think I've seen everybody here. I was the only late person. There they are in the back. And then we have some excellent undergrad students, Joy Averson and Radu. So those are sitting in the back there. And of course, we also have the requisite remote affiliates that will be working, some logging in and working remotely, some of them just working on the same data sets and wanting to know what's going on. We have Bing from Columbia University, Doug Jones from Lincoln Laboratory, a linguist who's spending part-time helping us with some of this work, and Jack Godfrey, who wants to just give us some feedback on another linguist so that we don't go too far in the woods, being mostly engineers on this. To put it in context, again, we're working on speaker recognition. So in the speech signal, as you've heard with the early ones, they're talking about the language parsing of the words themselves. And you'll hear the next talk talking about Arabic speech recognition, trying to extract the words from it. We're focused, just to kind of get everybody on the same page, we're focused on recognizing who is speaking from the speech signal. Now, as I show here, traditionally for extracting information from speech, whether it's the words, the language being spoken, or the speaker, we've tended to treat these as parallel streams where most of the information is just pulled from the speech signal and then a different process works on trying to extract out the different levels. But as these techniques mature, most notably speech recognition and speaker recognition, we're starting actually to see a merge between these, trying to use information extracted from different types of levels of information to make our decision. And that's the main goal we're trying to get at, as I'll get into in this overview of trying to use different levels of information to do and improve speaker recognition performance. Now, a bit of a motivation here. If you think a bit about how you, as a human, recognize speakers, you use a hierarchy of cues for recognizing people, most notably familiar speakers. Now these cues tend to go from what we call high-level or learned cues to low-level or most notably physical traits. At the highest level, we have things like semantics, diction, word usage that you might use. Someone always says a particular phrase or turn of phrase. At middle level, you might have things like prosodic and rhythm, how a person speaks. Do they go up and down? Are they very excited or what? And at the lowest level, just how do they sound? What's the acoustics of their voice? Is it nasally? Is it deep? Is it bass or what? Now, for an automatic system, you can imagine using all these, but they also tend to track of going from the most difficult to apply at the top. If we want to do automatic recognition of some high-level features such as the diction and word usage, we have to extract out the words reliably to use them. And the prosodics, we have to get out super-segmental information about the prosodic stream. And the lowest level things about the acoustics tend to be the ones that are most easy to automatically extract and apply. And in fact, they're the ones that tend to dominate all the automatic systems that are out there today because they're easy to apply. Although there's no one specific feature that we can extract out, that's the one that is tended to be the one used in modern systems. So I just said, our current recognition systems that are out there, which are doing well in terms of performance, rely on short-term, low-level acoustic information about the sound of the person's voice, not really relying at all or using profitably any of the higher-level information conveying speaker identity. But we know, as I just went through, that there's many different levels in there, whether it's the word usage of idiolect, pronunciation, prosodics, idiosyncratic nature of saying words or laughs or even non-lexical types of sounds. And of course, there's been some evidence. What really got us rolling on this is there's been some recent evidence of automatic systems that have been able to exploit and use these different levels of information beyond just the low-level acoustics to actually do some speaker recognition performance. Most notably, Doddington looked at and was able to use word idiolect to actually get some speaker recognition performance. Walt Andrews and Joe Campbell and others were able to look at using phonetic streams to do some automatic speaker recognition. And Fred Weber and Barbara Peskin and their Dragon Systems looked at using prosodics and some idiolect work. So we have evidence that we can use this and rely and try to integrate it in with our current base systems to actually improve our performance. So in fact, that's the objective of the SuperSID team, is to analyze, characterize, extract, and apply these high-level information sources that have not been used to date or used effectively. Our approach is we want to first, since it's a new area and we're looking at different features, we need to analyze and characterize the high-level knowledge sources with respect to the speaker. Some way of coming up with tools of saying, do we think this level of information is conveying something about the speaker that is unique to that speaker? Perhaps looking at things like speaker entropy and so forth. Then we need to derive the new features and classifiers. How are we going to extract these from our raw data, come up with features that convey the information that we're interested in, and classifiers to be able to classify or detect that information in from the features themselves. And then, of course, to apply the features and classifiers to a task. Our task is going to be the text-independent speaker detection or recognition using the switchboard 1 and 2 corpora, which are telephone conversational speech data. We're primarily going to be focusing on switchboard 1 because we have this automatic and manual transcripts available, and SRI has provided us with a huge volume of prosodic markups for that at the word level and interword level using automatic speech recognition transcripts or true transcripts. So we have a lot of raw data that's giving us this information. We now need to parse through it and figure out what we want to use. We have a well-defined evaluation paradigm. We're going to be using the NIST speaker recognition detection error trade-off curves, where we look at the trade-offs between probability of miss and probability of false alarm for a detection task. So we're going to be using that to measure how well we're doing for our baselines and have we improved our performance by using these high-level pieces of information. This is actually going to be using the extended data tasks from the NIST evaluations, which have about anywhere from 2 to 45 minutes of training data parsed up. We can look at using short amounts of training, large amounts of training, and about 2 minutes of test data. So this is a well-defined evaluation paradigm that we've used in the last 2 or 3 NIST evaluations. Now, we're going to focus in at first on a hard subset. I'll show some performance later on briefly just to show you that we're going to focus in on an area where the acoustic system is having trouble, most notably in mismatched situations when the acoustics between the training and testing are not matched up, and we see that it's actually having trouble. This is primarily where we hope these high-level pieces of information are able to come in and augment or at least improve our performance when the acoustic system is not doing as well as we'd like. Our goals by the end of the workshop are threefold, one of which I have grayed out because it's actually more of a long-term goal that sets a framework of where we'd like to be. The first is we want to define new features and classifiers using this high-level information. So there hasn't been a lot of work published. There's been little bits and pieces of it out there of people trying to use these high-level information, primarily because they're difficult to extract and hasn't been data available in a reliable form for people to use and have a common evaluation paradigm. We hope to change that by having the SRI data marked up and features extracted and lay those out on the table for us to look at this summer and to put out some possibilities for others to pursue. We also want to outperform our current baselines, which we're going to define in 4 different areas for high-level information. The last one I grayed out because it is a goal, but it's probably not going to be attainable this summer, is to establish new techniques for fusing the different levels of information. This summer's goal is to look at the different levels of information and what features and classifiers we can use to extract it out. It's going to be a very important question once you've extracted them out. How do you fuse them together? When do you know to believe what level of information to make the best decision overall? That's a very tricky question. Just simple fusion techniques that are out there probably won't work, although they might help us to some degree. But that's going to be the follow-on once we have all the tools laid out in front of us. So we've organized our team through team meetings and so forth that we've had in March and in May into 5 subgroups that we want to start off having us to make headway into the different levels of information. And they roughly follow the levels of information that I talked about that are conveyed that are not currently being used. You notice we don't have acoustic information here. We're explicitly avoiding using any acoustic information except maybe as a baseline comparison or for fusion purposes. We really want to focus on the levels of information that have not been used to date. So we have a prosodic subteam, we have a phonetic subteam, an idiolect subteam, linguistic subteam, and then the last one is more of a catch-all, the fusion subteam, which is going to look at trying to fuse these together, if not in the ultimate low way that we would like, just using simple MLPs or some way that we can aggregate the different levels of information together to bring it into a coherent whole. And if you note for each of these, I've listed some baseline that we have. What we wanted to do for the different sub-teams or subgroups that we're looking at is actually have some baseline that's currently been published that people have looked at. So we have something to know that this is what people have been doing, whether it's the right or wrong way or the best way. People have actually had out there and published on using. And we can say, this is where we started from. Have we improved upon that? Maybe we will, maybe we won't. But we need some baseline to know whether we've gone ahead or fallen behind. And lastly, I just wanted to give you a feel of the performance that we're currently seeing in some, this is a rough idea of the baseline that we're seeing from one of the evaluation setups. This is from the extended data training task of the NIST evaluation. Here we're using 8 training conversations, which roughly about 16 to 24 minutes of training data. And what we're seeing here is, this lower black one is our performance of our baseline acoustic system. And we see that we're doing exceedingly well. The acoustics do well under most conditions and still give us levels of performance. What we see here is the performance of using the phone n-grams, where we're not using any of the low-level acoustics. We're purely looking at n-grams of the phonetic sequence itself. This is the word n-grams here, where we have an equal error rate that's somewhere around 15%. This is an equal error rate about 7%. And the acoustics in this case are giving us an equal error rate around 1%. And then using even higher level, more abstract information, such as conversational patterns and linguistic patterns of the conversation itself, we're getting error rates that are much higher than that. What I really wanted to show from this was that we have a lot of improvement to do, but there is speaker recognizability that it can be obtained from these different levels of information. Now, if we fuse these together, we can actually improve this baseline slightly. As I mentioned, this is going to be our core task that we're focusing on, although we're probably going to focus in on areas where we're actually getting these errors. What are the patterns that are actually giving us these errors as low as they may be, about the 1% equal error rate, and to see if these different levels of information can be fused to help improve just those areas where we're getting our performance drop off in the acoustic system itself. And that in a nutshell is the SID team, all the tasks that we're going to be taking. I'll take questions or Anything else? Yeah.
You said that you're not going to be trying to improve the acoustic system. What is the system that you're using as a fixed system?
It's a Gaussian mixture model, universal background model system, the one that produced that black curve on the last step. So what we're going to do is bring in the scores from that for the different tasks and use that in fusing at any point in time. Sanjeev?
One of the questions that employees high-level source of information, you need more data from the speakers.
Yeah.
Do you have any plans to do like a curve which shows as you get more and more training data from the speaker, how much they know?
Yeah, so I didn't make that as clear as I should have, perhaps. The extended data task paradigm is used by the NIST that we're going to be mimicking here, that is used in the NIST speaker recognition evaluations. As I said, there's between 2 to 45 minutes of training data. Turns out that corresponds to having 2 minutes of training data. There's a task where you can get a depth curve, 4 minutes, 8 minutes, 6, something along those lines. So you can actually see at what point, how much information do you need, how much speech do you need for training. And as we've seen before, there's going to be a trade-off. As you get less data, maybe only 2 minutes of training data, things such as the idiolect may not help you as much as they will help you when you have 16 minutes of training or 45 minutes of training. So we will be producing curves that have performance as a function of training data. That is our hope toward the end of the workshop. Yeah.
I was wondering how much does the performance of your sort of high-level linguistic systems depend on the performance of your low-level, more acoustic systems? Because if they are, well, I guess the more independent they are, the more guaranteed you are that something like voting would really help you. Whereas,
right. So they're not directly related to the low-level acoustic systems because the low-level acoustic systems are extracting out from the speech signal itself. They are related more indirectly in the sense that, of course, a speech recognizer or a phone recognizer is working off the same acoustic signal to derive its sequence and so forth. We're hoping that it's more abstracted away from the low-level acoustic signal so that it would be different information. We have found from some fusion experiments that we've run this last spring on the different levels that it indeed is giving us complementary information, just using simple MLPs, and that's what we hope to keep going on this summer.
A clarification question.
Yeah.
Your approach is a generative approach. I didn't quite see how you actually do the task. Is it generative or experimental approach?
For the classifiers?
Yeah. So I would have thought, I'm not a speech person, but I would have thought that speak identification, we're trying to discriminate between the population of speakers.
Right, we're doing, so the task itself is a speaker detection task. So what we're trying to do is saying, I give you a proffered ID of a person, I claim to be Doug Reynolds, I give you an utterance. And I say, are these from the same speaker, yes, no. So we're doing the detection task as opposed to the identification task, which is this unknown utterance coming from Doug Reynolds or Barbara Peskin or Joe Campbell or Walt Andrews? So we're doing the detection task, not the identification task. So we are, it's more of a, are these from the same speaker? Yes, no. So I don't know if that answers your question, but discriminate. It's discriminative in the sense that you have to discriminate, is it this person from the rest of the world? It's not the identification task of saying, who is it out of this known set of closed set of speakers?
Yeah, I was really wondering which sort of technique is sort of underlying your approach.
Oh, the classifiers?
Yeah.
Right. So the main approach that's been used for the high-level informations have been simple n-gram approaches. So they've used an n-gram language model for the enrolled target speaker. So take, for example, the words, the idiolect. It would take the word sequence coming in, train, let's say, a bigram from that word sequence itself for the target speaker using all of his training data, let's say 30, 45 minutes of speech. Then we train a background model from a large amount of other speakers, hundreds of other speakers. We'll then do likelihood ratio tests at the end. An unknown utterance comes in, we score that unknown sequence against the bigram from the target speaker, the bigram from the background set or the background model, take a likelihood ratio between that, and decide is it high enough match to say that we've detected this speaker or not. Now, those have been the techniques that are used so far. We think they're it's sort of the hammer-nail problem. You got a hammer, everything looks like a nail sort of approach. We don't believe that's the best technique, but it's the one that so far has given us baselines out. That's the other thing we want to look at is coming up with more sophisticated models if that need be.
You know, one of the issues here is that in terms of, is this Joe, kind of a biometric sort of application?
Yeah.
One could assume that the background noise associated with that's controlled and manageable and very low. So the question would be in the broader problem, based upon the multiple ways of doing speaker ID that you, in your graph that you had, what's the impact on a noisy environment? You know?
We don't know that directly. The hope here, so in this database itself, switchboard is relatively clean, so we don't have that as dimension. I can say for the acoustic information, the base acoustic signal, it degrades as the noise increases, primarily as a noise mismatch between the training and the test utterance.
That would make sense. What about the others?
The other ones, we don't have the information there directly, but the hope is that they will be a bit more robust because they might have more constraints. For example, it's a constrained vocabulary, so maybe the speech recognizer keeps putting out the correct word sequence. Or, more importantly, not that it puts out the correct word sequence, but it's consistent when it puts out its word sequence. I don't care if the speech recognizer keeps calling cat dog. Just keep calling cat dog all the time because these n-gram approaches, at least as we're currently using them, are blind to the exact word sequence. They're more wanting to make sure it's a consistent tokenization that comes out. So there's two levels that we hope that these high level will come into play. One is they don't have to be exact, they just have to be consistent. And two, the constraints that can be applied to phone and word recognition and so forth might help in the noise
Well,
situation.
if you looked at the graph that you had in terms of your black line, I think the average error rate was like 1%.
Yep.
Down there. And probably implying a clean environment. So if you look at the black curve relative to a noisy environment and how that degrades, and then looked at the impact of the red, blue, whatever the other colors are, all that might be an interesting.
Yep. We thought of that we were trying to figure out how we can find this subset where a subset of data or data set we can look at where we can show for exactly those reasons when we expect these high level things to kick in and give us the performance boost we want. One of the difficulties with the data set we have, the reason we could not pursue that this summer is that we have the automatic speech recognition transcripts already online. So we're not rerunning speech recognition on these hundreds and hundreds of hours. So that might be something, once we establish the tools, that we do want to go back and get a speech recognizer or the phone recognition and actually reproduce those as we either synthetically or actually have noise added to the signal itself. Ron?
Yeah, just a question. You know, traditionally for the evaluation for the amount of data used for training, you're given a 2-minute set, a 4-minute training set, an 8, etc.
Yeah.
Have you any plans of looking on backing that off, where you would have a full 16-minute set, but you would develop the tools to try to say, well, I really can do just as well if I take this 7-minute subsection of that. In other words, trying to decide which of the extra data you should use and the rest thrown out because it's just going to give you data that you've so well used already, it's not contributing anything.
Not this summer.
Not this summer.
Very, very important question. This summer we're going full bore with what we have we're going to use and run through that all. Yeah, Jeff.
I'm just curious, so why is it in the case in these SID systems that for the acoustic only model, meaning, for example, the Gaussian, it's not the case that time information is useful? Because it's not, you said still that the baseline is just a GMM. And I know, I'm sure that people have tried this, but why, for example, has time information not been shown useful for SID?
I don't think it's been shown that it's not useful. It just hasn't been exploited in the right way. The current framework of frame soup, just extracting out frames at a time of data, which is the current same front end that's used for speech recognition and so forth, hasn't been exploited as much. I don't know that it's been shown it's not.
It's kind of amazing because any permutation of frames would give you exactly the same score.
Yeah, it's great.
Part of it may be the evaluation regime, because before people showed that you could get information from the phonetic content, the problem of devising, I mean, you basically would have to have people say the same thing in order to extract the identifying information. And I think we more or less accidentally stumbled on the method of using temporal information in the form of phone streams, very weakly constrained phone streams, which permit permitted the phonetic information to come through and still allowed you to extract from the difference in what's being said. I think if the focus had been on extracting phonetic information a long time ago, it might not have been the case that you would just go with Gaussians with no time constraint.
That's right. I mean, the text independent too tends to lend itself to bias you away from that. Text dependent systems will always implicitly use the sequence information by doing dynamic time warp and other things. The text independent, without those higher level markings of a word or phone sequence, people didn't have those in play. I think you're going to see it coming more into play now because people believe and have reliable speech recognition systems to use as we're showing to bear in a text independent environment.
And talking of reliable speech recognition, what is the accuracy of the transcripts that you do have?
We have three types of transcripts. We have manual transcripts, which in so much as people agree with what people write down is 0% error. We have Dragon's transcripts, which are nominally 20 to 30% word error rate on switchboard 1. Very good speech recognition. And we have BBN's real-time system, Biblos real-time system, which they gave out to allow use in this last NIST evaluation. Real-time system, I think it's in the order of 40 to 50% word error rate. No, my head moves this way. Look at my finger.
You mentioned baselines for each of the 5 research subgroups this summer, and I think I saw the baselines on that last plot except for one, and that was the pitch distribution.
Well, you didn't see the baselines on that last plot. That was a nice sleight of hand. There's some of the baselines on there. We don't have all the baselines plotted out, but no, we don't have the pitch distributions laid out.
Do you know even roughly what kind of,
Pitch by itself, just using the pitch distributions, I believe, I can't say for the extended data task, for 2 minutes of training data, would nominally give you about 20 to 30% equal error rates, if that good.
When you go to the higher level data, where it may improve you, give improvement with a uniform data set like switchboard 1, where it's all casual conversation, how do you guard against getting into a problem where, say, it was a mixed data set, say it was part ADIS type, interactive, and part switchboard type free conversation, where you'd expect certain word patterns in one and they would be completely messed up by going to some task-oriented.
Well, that leads into this notion we're talking about fusion. At one point, how do you know when to believe which one that's happening? So if it gets to the case where it just says, I'm not getting enough information, or this doesn't look like the type that I was trained on, something along those lines, can you know when to fall back to the acoustics only and pull away from the other one? But I don't know. At this point, there's no corpora that exists that have that mixed type in. Yeah, Rich?
I was just wondering, you mentioned that you don't necessarily require that the recognizer, let's say, get the right answer. But those curves that you showed, were those results for automatically recognized phonemes or words, or were they for the manually?
Well, the phonemes are always automatic. So the phonemes, all we're doing is running a phone loop. So that's always the case. We don't have a hand transcribed set to use on it.
Oh, okay.
The word was exactly, yeah, in fact, it was the BDN, 50%. We found that going from manual to the 20% to the 50% had surprisingly little loss in performance. It went from like 11% equal error rate to 15% equal error rate with that high of an error rate in there.
Wow.
Yeah.
You might have answered this already. The error rates that you showed on the last slide are for what kind of contrast set of speakers? Obviously, the number of speakers you're trying to distinguish your target from, and who those speakers are, how similar they speak.
So it's
will have an effect on this.
Right. It's same gender. It's often the same corpus. So you never try to. It's always same. So what the issue with the detection task is, you have to ask what's your imposter data that you use to run against this. And the imposter data was always the same sex, so we had no cross-sex trials. We could do it as a gimme. If you want to improve your performance, that's a good way to do it. It's all from the switchboard database, so it's all conversation, so that the style and everything's the same on that. Other than that, it wasn't controlled. There was no going in trying to find who's the person that's most similar to this. It was actually just selected out of a large set of 500 speakers, I think. So
So you have 499 imposters?
Not directly. It's subsetted out. In essence, it's the same as having about 499. They're drawn from a pool of 499. It's a random subset that's pulled out. That's what it said.
But again, you have to think of this is a known target speaker that you're looking for against the world. It's not that you're testing against the other putative target speakers.
Yeah, understood. But if you're trying to pick somebody out from 5 billion people,
Yes.
your chances of getting a false alarm or a miss, depending on where you set your threshold, are much higher.
No, it's not. It's independent of the size of the pool, as long as you
It's
don't
big
take
enough.
advantage of the specific pool.
It might actually be lower for background model, but.
Right. The big assumption we're making here is that the 500 some odd speakers that we have represented in switchboard is a not unbiased population that we're testing against. Maybe that's what you're getting at. That if we scale this up to 5 billion, it could be this 500 was just an anomaly sitting over to the side, and 5 billion bring up a lot of other issues that come into it. Very well could be the case. But given that you believe that the population from which you're pulling your imposter trials from is representative of the population in general where you're going to use it, then, as Rich said, the performance is independent of the number of speakers that are in that imposter distribution.
I may be missing something obvious here, but it seems to me like if you scale up to 5 billion, your chances of finding your target's identical twin in there is much higher. Right?
Again, we don't know that. That's the assumption.
You just have a denser distribution of darts around bullseye, so you have less discriminative power. What am I missing?
What you're missing is, in that case, the chance, so what you're saying is that if that identical twin happens to be the speaker, and you say, is it this person, you're going to make a mistake, of course. And the probability that that happens to be the speaker you're looking at is some small number, and it's fixed. So it doesn't depend on the size of the population.
Well, let's take this offline.
I think we need to move on to the next one.
Yes, thank you.
Okay, so I'll introduce the fourth and the last project for this workshop, which is Arabic speech recognition. I'll first give you an update on the state of the art of current Arabic speech recognition and what the problems are that we're facing, then describe the individual projects that we've chosen to work on over the summer and explain why we're working on them and what we're going to do. And then finally give you a summary of our high-level goals. But before I go into that, let me just briefly introduce the team. So the remaining senior team members are Jeff Films from University of Washington, John Henderson from MITRE, and feel free to raise your hands as I go along, Mohammed Normani and Rich Schwartz from BBN, Pat Schoen from UOD, our students are Surin Das from JHU, Gangji from UW, Melissa Egan and Frank Lee are our undergraduate students, and we also have 3 affiliates, Dimitra Bergiri from SRI, and Maria Stendorf and Ivan Velika at UW, who will be working remotely and for free. So we're glad to have that additional manpower. And so there have been some previous projects on Arabic speech recognition, and the 3 outstanding projects are the 96-97 NIST Call Home evaluations, which was evaluation of conversational speech recognition, and Arabic was one of the tasks. There's been some work on dictation for Arabic, mainly at IBM, and more recently there's been the BBN Tiles and Tab project, which is recognition of broadcast news speech. So overall, there's been fairly little work compared to other languages like English or Spanish or even Mandarin. And there's also a serious lack of speech corpora and standardized resources that we can use for this task. So the current state of the art is as follows. So the best systems are currently located at BBN, the Tiles and Tab system, and the conversational speech recognition system. Performance on broadcast news speech is quite reasonable, with a word error rate of about 15%. On call home, on conversational speech, it's a lot higher. And the word error rate on conversational speech for Arabic call home is also a lot higher than the word error rate we find on comparable data for other languages. So on English, for instance, the best systems currently achieve around 30%. So that was what prompted us to really focus on the recognition of conversational Arabic during this workshop, and not concentrate on recognition of raucous speech, for instance. And it turns out that the only resource that we have available for this kind of work is the LSE Arabic Call Home corpus, which is Egyptian Arabic dialectal speech. Alright, so there may be two sources for the high word error rate on call home. One of these problems may be of a more generic nature and may characterize speech recognition in general and conversational speech recognition in particular, which is there may be noisy signals, high rates of disfluencies, and so on. And people just haven't spent as much time working on Arabic as they have working on English, so there hasn't been as much engineering effort that went into that. We're basically going to ignore that class of problems, and we won't work on tweaking the standard ASR methods like speaker adaptation and pre-processing for this particular task. That's not what we're here for. Instead, we're going to address the other two questions, which is to what extent do we actually need language-specific models for Arabic, and how far can we get using purely language-independent methods? So what are the possible models that we could use for Arabic, and does it actually make sense to use something that's specific to the language that we're working on? Right, so these are the three main problem areas that we've decided to work on. The first problem is the lack of training data for conversational Arabic. The second one is the mismatch between the spoken and the written representation of Arabic. And the third problem is morphological complexity.
The mismatch has to do with dialect, or?
The mismatch between the spoken and written representation, I'll explain that in a minute. No, it's actually different. So the first problem is that there are large differences between what is called modern standard Arabic, which is a formal standard common throughout the Arabic-speaking world, which is mainly used in the media, in newspapers, and for any type of formal communication, as opposed to the dialects which are used in everyday conversational speech. Most of the dialects are not written, so any kind of written material that you typically find for Arabic is modern standard Arabic. So that gives us very little training data that we can use for our call home task. And one of the questions that we're trying to answer is, can we use out-of-corpus text resources to improve language modeling performance on call home? And the way we're going to use that, to address that problem, is to find text resources that are freely available on the web, try to classify them on the dialectal format scale using automatic statistical methods like part-of-speech-based n-grams or unigram frequencies of dialect words, and to subselect the text resources and integrate them into our existing language data, and compare that to using purely call home data. So far we've collected text resources and have acquired the tools and data for doing part-of-speech tagging for Arabic, so we're all set to get going on that. Alright, so the next problem is the mismatch between the written and the spoken representation of Arabic. So Arabic is written in script, and the script contains regular letters for the consonants and for the long vowels. The short vowels, on the other hand, are not written using letters, but they're indicated by diacritics that are placed either above or below the preceding consonants, and I've given you an example here. So this is the non-diacritized form, and this is the diacritized form, which contains short vowel marks, and also markers for consonant doubling and similar things. So most of the texts that you find for Arabic are actually not diacritized. The only exceptions are the Quran and some beginners texts, but usually text resources are not diacritized. So the vowel marks are absent in your training data. And of course the problem is, how do we train acoustic models for short vowels, given that we don't know where they are in the data and what they are? It also happens that due to the absence of vowel marks, there are a lot of word forms that look identical in the script form, but they can be pronounced in different ways. And this kind of lexical ambiguity also leads to weaker language models, because they can't be as strong as on predicting words, because the same script form appears in lots of different contexts. So the question is, does that affect the word error rate at all? And the answer is yes. We actually do have numbers for both systems. This was an experiment that was done at BEN, where one system was trained on the graphical representation of the graphings, so no explicit short vowel marks were used in that system. And we have a system trained on the actual phonetic representation. This was for Arabic called home, where we have both the script representation and phonetic representation. And as you can see, there's a difference encompassing absolute between the two word error rates. Alright, so the way we're going to address that problem is to develop methods for the automatic prediction of vowel marks from the unvowelized text. This is also something called automatic diacritization. And our goal is to use the output of this automatic diacritization process as training material for speech recognition and to compare it to the script-based version on one hand and the true phonetic representation on the other hand. And there are a lot of questions associated with this, such as how to determine the appropriate amount of data needed, how quickly we can bootstrap such an automatic diacritizer for completely new Arabic texts, and how well we actually do using that kind of output. So in our pre-workshop experiments, we tested a commercial diacritization tool. There are actually some tools around for doing this kind of work, but they were all developed for modern standard Arabic, whereas we're going to work on dialectal data. So the tool that we tested achieved around 80% accuracy on modern standard Arabic, but on for home dialogues it dropped to around 50%. Then we tried to develop our own automatic diacritizer for Call Home. These were experiments that Don did, and he did a bunch of different things using different learning methods, different data sets, and also word level as opposed to character level prediction methods. And I'll only present one experiment, which is the one that we're directly going to build on for our work in the next couple of weeks. Where we trained on the EVA 97 data and some additional LBC data that we got about 2 weeks ago, and tested on the training set that we're going to use for speech recognition. And on that set, he achieved around 77% accuracy using maximum likelihood training methods. And it turned out that most of the errors were on unseen words that weren't in the training set that he used. Okay. So our goal for the workshop is to improve these prediction methods and then basically fill in the question marks in this table where we compare the automatic diacritization output to the graphing-based system and to the true phonetic transcription. And we're going to do this both for Call Home and also for the Broncos News corpus. Now in this case we don't have the true phonetic transcription, so we can only compare it to the graphing-based system. Right, the third problem that we're going to work on is concerned with Arabic morphology and the problems it causes for speech recognition. So Arabic words have quite a complicated structure consisting of a root which consists of a sequence of 3 letters, a pattern that is interspersed with the consonantal root, and also affixes and particles that can attach to the word. So this gives us quite a large number of possible word forms, which is not a very good thing for a speech recognition system because it creates problems training robust language models, robust language model probabilities for all possible word sequences. And typically it also leads to a large number of out-of-vocabulary words. So this is a problem that besets all morphologically rich languages and speech recognition for those languages. So it's a problem that's not just specific to Arabic. So our proposed approach is to decompose words into smaller units, morpheme-based or morpheme-like units, and to train language models based on those units as opposed to word forms. Now there has been some previous work on morphologically rich languages and using morphology-based language models for them. And most of these approaches have failed. And some of the reasons for that is that morphemes were both used as acoustic units and as language modeling units. And the benefits that were seen in using morpheme-based units in the language model were offset by the increased acoustic confusability, because most of these morpheme-like units are fairly small. So another thing that was found was that the normal n-gram context that we use in speech recognition, the bigrams and trigrams, were not actually sufficient for doing word prediction in this context. because all that was achieved using diagrams and trigrams was to predict the probability of an affix, for instance, given the stem. So we're not going to take quite the same approach, and we'll try to circumvent those problems. So in the acoustic recognition lexicon, we'll continue to use complete full word forms, and we're going to use the decomposed language model purely at the language modeling level. And the approach that we're going to take is a rescoring approach. So our baseline system is going to be the BBN recognition system, which contains the full word forms, and then we'll rescore the embed lists and lattices using the decomposed language model. So this is what the proposed language model is going to look like in more detail. We call it a factored language model. So assume for now that a word in Arabic is equivalent to a combination of affixes, roots, and patterns, and that a trigram probability, for instance, for a word given to previous words, then decomposes into the combination of these three different factors given the combinations for the previous two words. And this can be factored as follows. Now the goal, of course, is to find appropriate conditional independence statements so that we can drop some of these conditional factors and simplify the model. Now that, combined with the lower cardinality of the random variables involved, so there are typically fewer affixes and fewer roots and patterns than word forms. Those two things combined are perhaps going to lead to a more robust estimation of language model probabilities. At least that's our hope and that's our assumption. So we may be able to make valid independence assumptions. So this equation supposes that F stands for the combination of the three components that I've shown before. And maybe we can make independence assumptions such that the individual factors are independent of each other, leaving the factors for the previous two words. Now our goal is to learn these kinds of structures, these kinds of independence assumptions automatically from data using structural learning techniques such as mutual information, Bayesian information criterion, or research techniques. Alright, so the work we've done so far, we've generated various different morphological decompositions for the call-home data using both expert knowledge, where somebody actually sat down and defined what the correct morphological decomposition is, versus automatic tools. We've got all the rescoring and structural learning infrastructure in place. And we've trained some simple factored language models just to test the infrastructure. We haven't used them for rescoring yet. We've also done some preliminary experiments on morphological learning, because one of the other things that we'll try to investigate is if this kind of decomposition helps for language modeling, can we use automatic tools to acquire the morphological components automatically, and or do we have to use expert knowledge to be able to get some gains? Right, so the plan for the workshop is to evaluate different decompositions, different methods for structural learning and for morphology learning. Something else that we're going to use is discriminative weight training to train appropriate weights for the different morphological components. And it also turns out that for some of these components we may be able to use different data sets for training. So, for instance, the root in Arabic words, which is a sequence of 3 letters, is fairly consistent across different dialects of Arabic, and also is similar between modern standard Arabic and dialectal forms. So we may actually be able to use much larger data sets for those kinds of components. And something else that we're going to look at is variable length n-gram modeling, where different n-gram orders are used for the different parallel language models. Alright, so to give you a high-level summary of our goals is, one of our goals, of course, is to improve the word error rate on conversational Arabic, which means, in this case, call home. But another goal is to test and evaluate genuinely new models, such as the factored language model, and see if we can get some improvements with those. This is going to be interesting because some of these methods may also be applicable to other languages, such as other languages that have a rich morphology, like Turkish, Korean, or Russian, for instance. Also, the automatic diacritization methods will be applicable to languages that use Arabic script or modifications of Arabic script, such as Hebrew or Farsi. And another one of our goals is to generate new resources to give some impetus to the work on Arabic speech recognition. We also have a rough time plan, but we'll probably modify it as needed, so I won't go into details. Basically, we'll do the simple things first, and then towards the end of the workshop, we'll do some of the more refined techniques, such as variable length angle modeling, and also apply some of the experiments to the Broncos news corpus, and then update our home system as we go along and continue to refine our methods. Okay, that's basically it. I'd like to take the opportunity to thank a couple of people who were extremely helpful with preparing this kind of effort. First of all, Fred, Sanjeev, and Laura for the organization and accommodating all our special requests and constraints. People at LDC and in other places who gave us data resources, and also a range of people who provided us with tools for morphological analysis, speech tagging, and so on. And also those people at BBN who were involved in bringing up the baseline system. And I'd just like to single out Bill Belfield and Owen Kimball also for coming along the other day and giving the tutorial talk. So that's basically it. And are there any questions? Yes.
This is really more of a question about Arabic. One of the reasons that people want to recognize speech is to understand what the speakers were talking about. And to a great extent, I think the meaning is, as I understand it, the meaning is available just from the consonant root, whereas the vowels actually come from other factors regarding harmony and the context that the word occurs in. And I was wondering whether the state of our ability to just model the context, the consonants that occur in the context, combined with our ability to model the association between these consonantal roots and meaning would actually allow you to just avoid vowels altogether and try to come up with just the root.
Right. That is not entirely accurate. So the root gives you the basic semantic meaning of the word. It's comparable to a lexeme. But the vowel patterns are actually not just due to vowel harmony or things like that, but also contribute grammatical meaning. So they indicate person, tense, voice, aspect, and things like that. So they actually do contribute to the meaning, and you can't completely ignore them. Now, for some applications, it may be sufficient to know roughly what speakers were talking about and to concentrate more on the information you can get from roots. This is not really something that we're going to look at during the workshop. Our goal is speech recognition, and we have the hard and fast criterion of word error rates. So we want to know how many words, what percentage of words we can recognize correctly, and that does include the vowels. So we won't simply leave that information aside. We're going to include that.
I guess it's a related question, and the question is that since modern standard Arabic is written without the vowels, why don't people consider having ASR output which doesn't have vowels? And I think it was Kathleen, someone mentioned that when you read modern standard Arabic, sure, a native speaker can stick in the vowels, but apparently you can't quite do the same with conversation. Is that true? Is there a number to it?
That is right. So in order to disambiguate the non-diacritized forms, you need to know the language and you need to have context. If you don't know the language or you don't have the context, then you don't even know how to pronounce the word. For some applications, it may be okay to build purely grapheme-based systems which do not include the short vowel information. For instance, for information retrieval, and this is actually what the BBN system does for broadcast news. It doesn't include the vowel information. So for information retrieval, this may be something that's perfectly feasible. And yes, I also remember Kathleen saying that for conversations, native speakers of Arabic weren't really able to fill in the correct vowels in all contexts. Is that right?
They have the freedom of not using the diacritics, with sukoons, whatever.
But
that's where it shows if someone is well educated or not educated.
Right.
So the person who's well educated may use the diacritics properly, but it's allowed. So the difficulty you're going to have is with the transcription. The transcription of the call home is done without, it's transliterated. So transliteration includes diacritics, but depending on how that transcribers heard it. And many transcribers, many times what they do is they correct it to sound proper, while the person may have not said it properly. So maybe one thing to do is to take the call home data and retranscribe it with the script. without any diacritics, transcribing it exactly as the person said it.
Yeah, we
Because at
actually,
this point you have data that's transcribed in transliterated form, not in.
well, so in Hong we actually do have both versions.
You have
We do
both
have the
versions.
transliterated form, and then the
Yeah,
script
we
form
do.
is rewrite from the transliterated form, so we do have that data.
I guess
It's not corrected, I
I was leading up to a slightly different question.
Speak up louder.
I was leading up to another question as well, namely that, like, NIST in its infinite wisdom decided to evaluate the full word form with the vowels.
Right.
But regardless of the wisdom of NIST, I guess the point that I was trying to make is, can you circumvent the vowels? And the answer I would say is no, because the acoustics have them. So if you want to recognize them, you have to do something about them.
That's why I brought up the consonant model. So the consonants are exactly what the power of your
Right, well, the graph-based system that I mentioned earlier on that BVN uses is trained just on what you find in the script, which is the consonants and the long vowels. And what was done was that the topology of the models was made longer, so you simply have more states in the model to implicitly incorporate the acoustic context. But it's only incorporated implicitly, so you don't have different models for different consonant and vowel combinations.
It's because there's also sort of an acoustic argument why you might want to include the vowels, even if you don't ultimately want to recognize them. Since, for example, you have acoustic models that don't contain the vowel information, necessarily that would mean that the spread or the variance of them would be larger. Whereas if you say you have a couple of models, each of which models specifically the vowels for each vowel-like word, and then you have a bunch of them, just the ultimate overall spread of that mixture would be smaller, which would lead to less acoustic confusability.
The only problem you may have is that the automatic diacritizer follows grammatical rules. And the spoken language doesn't follow necessarily grammatical rules.
Well,
You may need the diacritics, but they may be done not automatically, because the automatic diacritizer will fix the problems of the spoken language.
That basically depends on our training data. So the automatic diacritizer that we'll be using will be a diacritizer trained on Home, so it'll incorporate whatever was in that corpus. And if people don't follow grammatical patterns, that'll be represented in the training data.
As long as
So we're not going to use one of these commercial tools that may be more rule-based, like what you're saying, but we'll actually use something that was trained on the corpus.
What Jeff brought up is the alternate pronunciation problem, which, if solved, could be applied.
Right, it's an extension of that, yeah. One more question?
The missing diacritics are just an example of ambiguity between the written script and the stream of phonemes that it maps to, which exists in every language to some degree. Do you think most of the techniques that you'll be investigating are specific to the diacritics problem, or would be generally extensible to that ambiguity in other sets of languages?
Well, in most other languages, you have the problem that the written representation doesn't really match the phonetic representation very closely, but all the phonetic segments are still somehow represented in the written form. Whereas in Arabic and in a lot of other languages, there are certain classes of segments that are simply missing from the written representation. So I think the methods that we'll be investigating are more specific to those types of languages, where it's a certain type of segments that are missing. But we'll see. It might be possible that some of those methods might also be applicable to general grapheme to phoneme mapping in other languages.
Well,
okay.
Thank you very much.
This ends the first part where we were going to tell you what it is that we're going to work on. And those who have been coming for years and are cognoscenti of this process, I think this is the best presentation that I've experienced in the last 8 years. And I'm very thankful that people took so much time. Maybe it's the technology, but it certainly has improved. All right.
I think it's the room.
Maybe it's the room. All right, and furthermore, we're on time. And Bill Byrne is going to keep us on time.
So it's fallen to me to tell you about the computers. I guess those of you who are not going to be here for the summer can go get some coffee or something.
There is fresh coffee.
There is fresh coffee.
There's coffee. There really is coffee. We did get coffee.
There's always this question that people talk about. You don't know how to describe
Just go right through.
Go right to it? Okay. So this is what the computer network servers and file systems look like for the summer. We have, starting at the top, we have 2 hardware RAID arrays. In particular, you'll be doing your experiments in 4 100 gigabyte file systems. And your home directories are on another RAID array. These are served from 3 Sun file servers. Their names are DC04, DC03, and DC12. Everything is connected by a gigabit Ethernet. And we have the workstations in the lab, which I guess most of you have seen already, and perhaps some of you have used our compute servers. We have 5 main groups of servers. 4 Linux clusters and 1 cluster of Sun Ultra Sparks. More about that in a moment. Our network is behind the firewall, and in the so inside the firewall you can get out. Outside the firewall, hopefully you can't get in except through the login server, which you have to get through by SSH. Also in the DMZ are the web server and the FTP server, and then there's a connection to the campus network. Fairly straightforward. Any questions?
Can you VPN out?
I don't even know what that is.
Yes, you can VPN out, you cannot VPN back in. So you can do it, but you won't get any results because you can't get the signal back in.
So you can't do
You're not, no, what are you give me a hard time?
Our team's directory is really WSO2, right? Not WSO.
Oh, sorry. Yeah, my apologies. WSO2. Yep.
Maybe you would answer this question. Did we get more machines this year?
More machines than
Last year?
last year? I'm not sure.
So they're faster, so if you count that as more, yes.
Any other questions?
Cool.
Yeah, no. Any other questions? Okay. Okay. So some general tips. The first thing is, please ask for assistance. The way the groups have been set up is we assume that there's a natural hierarchy with the graduate students at the top. So you should always go to your graduate students because they know far more than you probably do unless you're a grad student yourself. If you're having trouble with the system, send email to help, that's the alias. And if you establish a correspondence with somebody in the support staff, just make sure that you always CC help so that everyone is aware of what's going on. We have, so to access the machines on these clusters, we have remote job execution programs, PMake and Customs. People in your group, if you don't know how to use these, will show you how to use them. Yeah.
Does the PMake work across the platforms from Unix, Linux, and back?
Yes. Okay. Although that's the short answer. The longer answer is you have to hardwire you have to set up your paths so that they work correctly, so that you don't try to execute a Linux executable on the site. We have dedicated computers for each group, and you should use the computers that were dedicated to your group. There's invariably some horse trading that goes on over the course of the summer. The way this is typically done is you say you need more computers, you go to your group leader, he goes to the other group leader, see who has a bit of extra cycles at the moment, and maybe you share. I want to stress that there's other work going on here at Hopkins this summer. We have many other projects in CLSP, and so please only use the machines associated with your group. These machines have not actually been allocated yet. That will be done this afternoon, I think, after we have the team leader meeting. Pay attention to disk usage and job size. If you fill up the disk, or if you start your machine swapping, they're not going to run any faster. The other thing is, for those of you coming from a Windows background, be careful about deleting files and directories. A Unix does not have like a little trash can where you can go and restore things. We do have tape backups, but given the many terabytes that are being backed up on a daily basis, it may take longer to go and retrieve the file than it would take you to recreate it. In other words, if you go and ask for a file, it may take days to get it back. So our backups are done to protect against catastrophic failures, not to, go back and restore individual files. So please be careful. Invariably, people do this. Don't use file servers except to move data. If you happen to see that one of the file servers is got a low load on it, that doesn't mean that you should go run jobs there, because everything will slow down. You can FTP to file servers to move data. If there's a problem with the machine that's in your desktop, don't hit the power cycle. Go contact somebody in the help group and they'll come fix it. And then finally, I don't know if you can see that, but we have terrible problems, just like everyone else, with malicious vandalism, or maybe not malicious vandalism, but please practice safe computing. Keep your passwords secure. Don't log in and don't set up a telnet window somewhere and then do SSH to the login server, because that people can observe what you're doing. Don't take your password and put it in a plain text file on the web server, like one group did one summer. They thought that was a good idea. The campus computers have been attacked very badly over the years. We've been safe from that because we have a fairly secure firewall. It's set up so that things overall will work well. You will no doubt experience some problems due to this over the summer. I apologize for this, but we need to have it. We need to have a certain level of security. That's pretty much it. Jacob, our system administrator, is here. When you all go back to the lab later, he and his support staff will walk around and make sure you can log in, and he'll tell you a little bit more about the systems then. When you ask for assistance, don't ask me. I actually don't know anything. I'm not quite sure why I'm here telling you this, but you should ask Jacob or his staff. So
Now, I want to say, besides, you've been to all 10 workshops. Charles said he has shown up at the meetings.
But I mean, I actually know nothing about it. So, any more questions?
What's the dash Q option for V4?
For what?
The file servers that are connected to, could you go back? So the file servers are accessible by NFS to the computer server?
That's right, yeah. Yes, everything is available everywhere. I mean, all the file systems are exported to all the machines. Okay, thanks.
Okay. Our administrator will tell you what to do.
Okay, most of the students who have been here for the past couple of weeks kind of already heard this, so I'll go through it quickly for those who are just arriving today. I just want to welcome everybody. I hope that everybody had a safe trip, obviously, because we're all here. Over the past several weeks, as Sanjeev and Fred both mentioned, there's been a lot of preparation that's gone into today and the last 2 weeks and the next 6 weeks. Some of you have communicated by email with some of us already, but I'd like you to have faces to put to names. And I also want to let you know that everything that has taken place over the last 2 weeks and that will take place over the next 6 weeks would not have been possible without the support staff who's working at CLSP this summer. First person is Conway Benishek, back here in the corner. And we also have some students working with us, Aaron Sachs, Smita Raman. They are available and will be down in the lab most of the time if you have any questions about stuff. I'll go into that in a minute. And also David Morrow is over here in the corner, and he's our webmaster for the summer. If you have any questions about the web page, anything that you want to put up there, be in contact with David, and all their email addresses are up on the website. When you arrived at either the Broadview or the Colonnade, wherever you're staying, you should have received a bag and a folder with a whole bunch of information in it. There is a booklet inside that looks like this. Anybody who didn't get one, we have extra copies. There's a lot of different information here about the campus, about Baltimore, places in the area. It's just basically a reference guide. There's information about getting keys for Barton Hall. There's information about the telephones that are available to you in the lounge and in the lab. So check this out. If you have any questions beyond this, talk to Smita, Aaron, Conway, myself. We'll try and help you out. Some specifics about that. If you do need keys still, see Aaron or Smita. They can get them for you. You'll be provided a key that will get you into Barton Hall on the weekends or in the evenings, and that same key will also get you into the stairway where there's access to the computer lab. There's a number keypad on the computer lab door. The combination to that is in this red booklet. In your folder, you also should have gotten a small brown envelope for you to put your travel receipts in. Anybody who's getting reimbursed for their travel, please put all of your receipts in there and turn them in to one of the 4 of us, and we'll get them processed and have the checks mailed to our office so that we can hand them to you rather than mailing them to your school address or work address. Many of you are also receiving per diem checks and stipend checks from us. The per diem checks will be issued on a bi-weekly basis, and we'll hand those out on Friday afternoons. The stipend checks will be issued and handed out on the last day of the workshop of the 23rd. If you're leaving early on the 23rd, let me know so that I can make sure I get that to you before you leave. I want to talk a little bit about security. The computer lab, the main door is locked. When most of the group is in there, the door tends to get propped open, and that's fine when a lot of people are in there. But keep in mind that other people have access to the building, and things in that room are not necessarily secure. So if you have your own laptop, make sure that you take that with you. If you have other items that you're keeping in there, there are file cabinets in there that have locks, and you'll have a key to the file cabinets, but we don't recommend leaving any valuable items in there. Also, on the lines of security, if you're working here late, especially after dark, which most of the groups tend to do, there is a security van that will take you back and forth from the Broadview or from the campus to the Broadview or to the Colonnade. You just need to give them a call, and information about that is in that red resource book. Please take advantage of that service. We haven't had any incidents yet that I'm aware of, but we also don't want to have any. And at night, the campus has some reasonable lighting, but it's also fairly tree covered on the pathway from here to University Parkway, so it's not really worth taking any chances. As I mentioned, there are telephones set up for you to use. There's one in the lab, and there are also 2 in the lounge. They are set up to make inter-campus calls and also local calls in Baltimore. If you want to make long-distance calls, you can use a credit card or a calling card, and those should be set up. If you have any problems, let me know. We have a photocopier upstairs in room 320 in Barton Hall. The photocopier that's in the computer lab belongs to the electrical engineering department. If you need to have photocopies made for any reason, bring them upstairs, send us an email. We can take care of getting those done for you. We have plenty of supplies, transparencies, other types of paper if you have any special requirements. Starting tomorrow and on Tuesdays, Thursdays, and Mondays, Tuesdays, Thursdays, and Fridays, we will have an afternoon cookie break for you. The students who've been here have already kind of gotten to share in those. We usually set it up around 3 o'clock or 3:30 in the lounge, and you can just kind of come in and take a break from your work and get a snack, socialize for a little bit. On Wednesdays, after we have the speaker, there will be a catered lunch, also back in the lounge. That will probably be right around 12 o'clock whenever the speaker's finished. Come back over to Barton 117, and lunch will be set up there. If you need to receive mail or
Don't we
faxes,
have something on Friday?
every other Friday, when we get the per diem checks, we'll also have a social kind of similar thing like the students are laughing because they had one last Friday with ice cream and cake and Sunday toppings and fun stuff like that.
We don't have ice cream every Friday?
No, we're doing it every other Friday.
Really?
So then you go away for a year.
Go away and things go to pot. We might have to restore it,
For you, I'll think that.
So keep your eyes open for new announcements.
Most of any announcements or changes will be up on the webpage, and quickly I'll show you that. There is a calendar up here, if I can make it work. Why am I not going home? This is not my homepage.
Click on the CLSP homepage. Further to your left. That one.
Anything regarding the workshop will be up under this first link here. And there's a calendar of activities that looks like this. If you go to the particular day and click on the day, it'll give you some details about the individual activities. And if there's anything else that anybody has scheduled, team meetings that you want to put up here, if you send an email to David Morrow, he can update the calendar. David, there's also a way that some of us can log in and update this, right? So that team leaders, if you want to do that, I can give you that information as well. Okay. If anybody needs to receive mail while you're here, you can have it sent to CLSP. Just make sure that it's sent to your attention. The people in the electrical and computer engineering department have a list of all the participants, and they'll direct the mail to us. There are some mail bins set up in the computer lab. Because there were so many people this year, we actually didn't have enough trays for everybody or enough space to put them all, so we just made 4 mailboxes, 1 for each team, and if anything shows up for you, we'll just put it in the team mailbox. The address for CLSP is on our webpage, so you can get that from there. Also, our fax number is on there if you need to receive any faxes. You can have them sent to that phone number. If you can, send either Conway or me or one of the students an email and let them know that you are expecting something so that we can be on the lookout for it. One of the other things in your folders was an application for a J card, which is our university ID card. If you fill that out and also the course registration paper behind it, we can get you an ID card to have for the summer. This will allow you access to our library and also allow you to check out books. And it will also give you access to our athletic center, which will be open for a few more weeks during July, and my understanding is that it's completely closed during the month of August. So, but you may want to double check that with the athletic center. And additional information about that is also in your resource book. Most of you who have walked back and forth have noticed that there are a few construction projects going on. Those should be mostly contained to where you see them now. They shouldn't be expanding any further than that. But if there are any updates, we'll try and make you aware of those in case you have to change your route over to campus. Our 2 closing days, as Sanjeev mentioned in his calendar, are August 21st and 22nd. We'll have presentations by all 4 teams on those 2 days. And then on the 23rd, we'll have cleanup of the computer lab and cleanup of the file systems and a final luncheon on that day. Any participants who are here who are not U.S. citizens
should make plans at some point early this week to just check in with our international office. They will want to take a copy of your passport and also your visa paperwork, just to have it on file. If you've already done so, don't worry about it. If anybody else still needs to go over, let me know and we'll schedule an appointment for you probably sometime tomorrow to go over there. It's just on the other side of Charles Street. It's not too far from campus. There were a few emails going around about the coffee station. Fred mentioned our wonderful espresso machine that we have. It is set up in the basement. We do have coffee mugs that we ordered for you. Some of you already have them. Those who haven't, if you see Smita or Aaron, they will give you a coffee mug and also a special pen to write your name on it. There are supplies down near the coffee machine to clean your coffee mug. There's an area that you can store it down there if you want. Probably better to take it with you. There are supplies down there for the coffee machine, milk, sugar, tea bags, whatever. If anything runs out, again, please let one of us know and we'll get it replenished for you. That's kind of all I have. Does anybody have any questions?
Is there a microwave?
There's a microwave up in 320, and if you're welcome to come up and use it if you want. If there is a great demand for it, then we may wind up moving it down into the lounge, and that wouldn't be a problem. Yes.
If there are no questions, I have one other announcement to make, and this is, don't get scared by this. Barton Hall has had recent problems with water leaks, and we've been told to keep an eye out for it. So there are these main pipes running in the 123 lab. If you see any of them dripping, please call security. I won't get into the gory details of what kind of disasters have happened, but we were told to keep our eyes peeled, and this is just, I'm just passing it on.
Well, thank you very much. This is the end of our session here, and I think you're supposed to walk into the lab.
Over to Barton 123.
And
the students can lead the way since they've been.
they'll tell you what to do when you get there.